Alright, so kinetic energy. Imagine an object of mass m at rest at a height h. If dropped, how fast will it be traveling just before striking the ground? So we use our kinematics equations to get a formula for v squared. So if we look, we've got our v squared equals v naught squared plus 2 times the change in x, or x minus x naught. Since v naught is 0, it was at rest, we cancel that out. And since our change in x is the height, and our acceleration was g, we would replace it as 2gh. This should actually say, 2a x minus x naught. So this whole part is replaced by h, and this part is replaced by g, which is how we get this. We can now solve this for gh. So we would get gh by itself by dividing by 2 on both sides, and that's how they get gh equals v squared over 2. So we're going to use that in a little bit. In this example, we dropped an object. So if you look, we've got the ball being dropped over here. While it was falling, its energy was constant but changing forms. Remember, we don't add energy, we don't take energy out unless work is involved. So if it started with GPE at its height where it started, it had height but it didn't have velocity. It was just GPE because it wasn't moving. Then, just before striking the ground, or in the example on the right, before hitting the hand, it only had kinetic energy, as it had velocity but no height. So now it hit the bottom, our height was 0, but it was moving. It had velocity. In between, it had some of both. So at the starting point, it had just GPE. Then it made its way down here, and it had kinetic energy because it was moving. So as it went down, GPE became less and kinetic energy became more. So now let's look at this from the energy perspective. No external force acted on the system, so its energy is constant. So that means its work was 0. There was no external force. Its original energy was in the form of GPE. So we've got our work was 0, and our energy original was GPE, which is mgh. So they canceled out work. They replaced the original energy with mgh. So now we want to solve for gh. So we would divide by m on both sides, which gives us this. So now if we look at our result that we got before, we said that gh equals v squared over 2. So now they took the gh and they replaced it with v squared over 2. And they made it equal to what gh equals over here. Now, to get the energy by itself, they multiplied by m, and they ended up with our equation right here, which is our equation for kinetic energy. You don't have to know all of this and how to get it, but this is how they got it. This is the one you need to know. Kinetic energy is 1/2 times the mass times the velocity squared. So the energy an object has by virtue of its motion is called its kinetic energy. Remember we talked if you're a kinesthetic learner, you learn by moving. The symbol we will be using for kinetic energy is Ke, and just like all the other forms of energy, it's measured in joules, J. So the amount of Ke, or kinetic energy, has is given by Ke equals 1/2 times mv squared. So as an object falls, its Ke always A decreases, B increases, C stays the same. So we just said it started with GPE, and in the end, it's going to have just Ke when it gets to no height. So as it goes down, it loses GPE. This goes down because the height is going down. So that means Ke needs to be going up. So it B increases. A ball falls from the top of a building to the ground below. How does the kinetic energy compare to the potential energy at the top? Well, we just said GPE is going to be the most, so our PE will be greater than Ke. What is the kinetic energy of a 12 kilogram object with a velocity of 10 meters per second? So now we've got our mass is 12, our V is 10. So if we've got Ke equals 1/2 mv squared. So now we're going to plug in our numbers. Ke equals 1/2 times 12 times 10 squared. So KE equals 1/2 times 12 times 100, which is going to give us 600 joules. So now the next one, they want us now to solve for the mass of an object which has 2,400 joules of kinetic energy when traveling at 6 meters per second. So now our KE is given as 2,400 joules. Our velocity is 6 meters per second, and now we're looking for our mass. So if we start with our equation, KE equals 1/2 mv squared, and we want to get our m by itself. Remember that multiplying by half is like dividing by 2, so we're going to want to multiply by 2, the reciprocal, to cancel out that half. So now we've got 2KE equals mv squared. And now since v squared is being multiplied, the opposite would be to divide by v squared. So we get our mass by itself. So now we've got our mass equals 2KE divided by v squared, which when we plug in is going to be 2 times 2,400 divided by 6 squared, which gives us 4,800 divided by 36, which gives us a mass of 133.3 kilograms. So now we've got a 3 kilogram object which has 45 joules of kinetic energy, so our KE equals 45. And they want to know about velocity. So again, we start with our equation. We want to cancel out that half, so we're going to multiply by 2. And we've got 2KE equals mv squared. And we want to get that v by itself, so we are going to divide by m. And to cancel out our square, we want to take the square root. So now our v is going to equal the square root of 2KE over m, which gives us 2 times 45 divided by 3. Gives us a square root of 90 divided by 3, which gives us the square root of 30. So now our final answer, v, is going to equal 5.48 meters per second. (18) If the speed of the car is doubled, the KE of the car is, so if we have our equation, KE equals 1/2 mv squared, and we are doubling our velocity, we're going to have KE equals 1/2 m2v squared. So if we square that 2, we end up with KE equals 1/2 m4v squared, which means this answer is going to be multiplied by 4, which means it will quadruple. Alright, 19. Which graph best represents the relationship between the KE and the velocity of an object accelerating in a straight line? Well, we know that the velocity is always going to be squared. So KE is not going to be constant as the velocities change. We know it's not A. We know they're not going to be going 1 for 1 in B because it's being squared. And as velocity goes up, our KE is not going to go down because it's going to increase. So we know it's not C, so that gives us D. And the square is what gives us this curve. Oopsies. Alright, the data table below lists mass and speed for 4 objects. Which 2 have the same KE? So what you're going to want to do for this one is you're going to find KE for each one of these, and the 2 that match will be your answer. So do that one on your own. All right, elastic potential energy. Energy can be stored in a spring. This energy is called elastic potential energy, so EPE. Robert Hooke first observed the relationship between the force necessary to compress a spring and how much the spring was compressed. So, K represents the spring constant. So that's, depending on the spring, that's a special number that goes with that spring. And it's measured in Newton meters. Newton per meter. X represents how much the spring is compressed. So that's the distance the spring gets pushed in. And it would be measured in meters, just like X is always measured. The negative sign just tells us that it's restorative. So if you put it in when it's compressed, it pops out to the same position it originally was. Think of a slinky. So the work needed to compress a spring is equal to the area under its force versus distance curve. So if we had force and distance, the area would be 1/2 times kx squared. If you think about a triangle, 1/2 times base times height. And since we have an x here and an x here, it's going to be squared, which is why you get this work right there, because work is force times distance. So kx squared times x, and then the 1/2 for the base times height. So we get that our EPE is 1/2 kx squared. This is the next equation that you need to know for energy. So this is what you need to know. You don't need to really know why we got it, but sometimes it helps you remember what it is then later on. And it's also measured in joules. So determine the EPE, the elastic potential energy stored in a spring, whose spring constant is 250 newtons per meter, and which is compressed 8 centimeters. So we're looking for EPE. We're given that K equals 250. And we're given that X is 8 centimeters. And remember, we work with meters, so that is 0.08 meters. Remember, a good way to remember how to write centimeters as meters is think of cents in a dollar. 8 cents would be written as $0.08 if you saw it on a cash register. So now EPE equals 1/2 kx squared. If you notice, this equation is just like the 1/2 mv squared, but it's just different variables. But you're moving it around the same way. So now our k is 250, and our x is 0.08 squared. So what you're going to get for that is 0.8 joules. Number 22, what is the spring constant? So now we're looking for K. It says our spring is compressed 5 centimeters, so that means X equals 5 centimeters, which equals 0.05 meters. And it has 0.65 joules of elastic potential energy stored in it. So that means our EPE equals 0.65 joules. And we are solving for K. So if we've got EPE equals 1/2 kx squared, we are going to multiply by 2 to get that half canceled out. So that cancels that one, and now we've got 2 EPE equals kx squared, and we're going to cancel out the x squared by dividing since it's being multiplied. So now you've got that k equals 2 EPE over x squared. We plug our numbers in, so now we've got 2 times 0.65 divided by 0.05 squared. And that is going to give you 520 newtons per meter. All right. Number 23, now they want to know what X is. So how much is a spring with a spring constant of 500 newtons per meter? So K equals 500 newtons per meter. Need to be compressed in order to store 1.75 joules of elastic potential energy. So our EPE is 1.75, and we are looking for X. So we've got EPE equals 1/2 kx squared. Multiply by 2 to cancel out our half. So now we've got 2EPE equals KX squared. Divide by K to cancel out the K. And then we're going to take the square root to cancel out that square. So now we've got X equals the square root of 2EPE over K. It's going to be the square root of 2 times 1.75 over 500. Which is going to equal square root of 3.5 over 500, which gives us the square root of 0.007, and we get that X equals 0.08 meters. Number 24. It says a 3 kilogram mass compresses a spring 2.5 centimeters. What is the spring constant? The only thing they forgot to mention in here is that it was dropping. So it's A equals 9.8. Our mass equals 3 kilograms. And our spring moves, our X is 2.5 centimeters, which equals 0.025 meters. So we want to look for K. The issue is we are not given our EPE. But we're given mass, and they forgot to give us, but they also give us our A. So if we remember sigma F equals MA, we can get our force. So force equals 3 times 9.8, which is going to give us 29.4. And if you recall from Hooke's law, it said that force equals Kx. So we can get our X now. We've got a force and we've got X. So we would divide by X over here, and we're going to get our K. So K equals the force divided by X, which gives us 29.4 divided by 0.025. And we get that our K is 1176 newtons per meter. So now in the next problem, they actually want us to, using the K that we just got, so K equals 1176, they want us to now find the EPE. So we've got our mass equals 3, and we've got our X was 0.025. So now we just have to do EPE equals 1/2 KX squared, and just plug our numbers in. So we've got 1/2 times 1176 times 0.025 squared. So we are going to get 0.368 joules. So based off EPE and KE, I'd like you to go on Edmodo and just write what you did or did not understand, and also to say if you were green, yellow, or red.